Very happy to introduce our next speaker, who is Colin Adams, me. This is the second to last talk in this session. We'll have another talk right after this by Alexander Mednick. I'm going to be telling you about hyperbolicity and volumes of charm bracelets. Now, before I do that, I want to talk a little bit about Lou. And a lot of people have been talking about Lou, and they've talked about what a big impact he had on them and lots of important things that he's done. Let me, he's written lots of books. So here's some of the books that Lou has written, many of whom were very important to me as when I was a young knot theorist. He had a huge influence on me. And many papers, and I'm only showing you books he wrote. I don't know how many books he edited. It just goes, the list goes on and on and on. But there's another side to Lou that fewer people have talked about, and that is his generosity and his just love of talking to anyone about knot theory. And so I want to mention in particular this conference that we put on about 5 times now, every couple of years, called the Unknot Conference. And you might think, well, Unknot Conference, that doesn't sound like a very interesting conference. But actually, Unknot stands for Undergraduate Knot Theory Conference. And what we do is we bring a bunch of undergraduates together with some researchers. And Lou is just wonderful at these things. He comes and he gives great talks and he shows them knot tricks. And the students are thrilled to meet Lou, given that everybody has heard of him who has any interest in knot theory. And so he's actually been wonderful about those things. I also wanted to tell you a story about what happened a little over a year ago. So a little over a year ago, Nancy Sherrick and Dan Margalit decided to organize a special event associated to the joint math meetings occurring in San Francisco. And what they did was they rented a theater, the Alcazar Theater, and they put on a math variety show, inviting a bunch of people to participate. And they sold tickets, not just to people from the joint math meetings, but people from all over San Francisco. And they filled the theater. And these are like, $25, $35 tickets. And they filled the theater. And then Lou and Allison Henrich, who spoke earlier today, were going to do some knot tricks. And so that was the plan. Unfortunately, Allison had an emergency and she couldn't come to the production, to the theater, to the meeting. And so Lou and her asked if I could fill in. And so without any practice at all, Lou and I got up on the stage together. And I played a police officer, and Lou was the criminal, and I was taking him to jail. And so we were hooked together, just as in this picture of Allison and Lou with the famous handcuffs. And we were hooked together, and I was marching off to jail. And I said, "Come on, you're coming with me to the Hooskow." And Lou says, "I'm actually not attached to you at all." And I said, "Yes, you are. We're hooked together by these handcuffs." And he said, "No, actually, we're not." And then he went to disentangle them, this move that you do to hook them loose. And much to my chagrin, instead of untangling us because something had gotten tangled, there was a bigger knot in the line. There was, instead of just a clasp that you normally have there was this big nasty knot there. I was looking down at this nasty knot, and Lou was looking down at this nasty knot, and a couple hundred people in the audience were looking down at this nasty knot that he had just created in the little handcuffs. And I'm thinking, oh, this is bad. This is our first knot trick, and it's already going down the drain. But Lou just looked at it and he goes, "Huh." And then he did a bunch of little things, and boom, it all came untangled, and when we separated. And the audience never knew that we had messed up the trick. They just assumed that was part of the trick. So one of the advantages of being in a situation like that is if you're in it with Lou, because Lou can figure it out when you're in these difficult cases. He can always figure out what to do. So anyway, and the whole thing was a lot of fun. So anyway, here is the levels of generality and specificity for different parts of the talk. I'm going to start off talking about hyperbolic knots, then I'll go down to knotoids, then more specialized to hyperbolic knotoids, back up to generalized knotoids, then down to a particular type of generalized knotoids called stake knots, then to bongles, and you think by now I would have run out of time, but remember, I'm the moderator, so I guess I can just keep going. So I'll just keep talking and think about other things to say as I go along. This first part of the work is with this group. These were undergraduates at the time. You'll see listed there their undergraduate institution and then their graduate institution. Many of them are now in graduate school. These were an amazing group of students. They're all incredibly talented and doing great things. So first, let me start talking about hyperbolic knots. As most people know, hyperbolic knots have a unique volume associated with them, a very effective invariant for distinguishing between knots by the Mostow-Prasad rigidity theorem. So if you look at the list of knots, the beginning of the list of knots, and here I have in red boxes the volumes, you'll notice there's a couple of knots that don't have a volume associated with them. The two braids, those are torus knots. They are not hyperbolic, so we just put a volume of 0 for them. The figure 8 knot here, the 5-2 knot, etc. And these volumes are a great way of distinguishing between knots. I need to define one other thing. We're going to say that a surface in a hyperbolic 3 manifold is totally geodesic if its projection from hyperbolic 3 space is of projective planes. So, sorry, of geodesic planes. So in particular, anytime you have a hyperbolic manifold, that means there is a projection map from hyperbolic 3 space down to the manifold such that the covering translations are isometries. And in this particular example, you see right here, this is the 935 knot. And here you see the Seifert surface for the 935 knot. And that happens to be a totally geodesic surface, which means if I lift back to hyperbolic space, I will see a collection of these totally geodesic planes, namely hyperbolic 2 planes living in hyperbolic 3 space that project down to that surface. Okay, so that's what I mean when I talk about a totally geodesic surface in a hyperbolic 3 manifold. I also want to define the following. I'm going to say that if I have a link complement in a 3 manifold M, I'm going to call it TG hyperbolic, just to emphasize the idea of totally geodesic. TG hyperbolic, if after capping off any spherical boundaries with balls, we won't actually have any spherical boundaries, but in the general case, you could. Shaving off any toroidal boundaries, so if you have a torus boundary, just remove it so that it becomes open there. Then there is a hyperbolic metric on the complement of the knot or link such that the higher genus boundaries are all totally geodesic. So in this picture that you see right here, I've got a thickened surface with a knot in it. And for this to be TG hyperbolic, the complement of that knot would have to be hyperbolic such that this outer genus 2 surface and this inner genus 2 surface were both totally geodesic. So that's what it would mean for this manifold to be TG hyperbolic. Okay, so Thurston has provided us with some wonderful tools to decide whether or not a manifold is TG hyperbolic. And so with a few minor exceptions, if you have a compact orientable manifold, 3 manifold with boundary, it'll be TG hyperbolic if and only if it contains no properly embedded essential disks, spheres, tori, or annuli. So this gives us a topological means to prove that a given manifold is TG hyperbolic, or to prove that it is not, if any of those exist in the manifold. So we'll use that. All right, now we're going to turn to nottoids. As I think many of you know, Tureyev came up with the idea of nottoids, where it's an equivalence class of generic immersions instead of a circle, as in knot theory, immersions of an interval into either. In our case, we'll only be interested in S2 or R2. Mostly we'll stick with S2, where the crossings are delineated and considered up to isotopy and Reidemeister moves away from the endpoints. So away from the endpoints, we can do our standard Reidemeister moves. And then we have this forbidden move that does not allow us to take any strands of the knot across that endpoint, either above or below that endpoint. So we're not allowed to move strands across the endpoint. And I'm going to call, for the purpose of this talk, those endpoints of the nottoid, I'm going to call them poles. All right, so just remember that we cannot cross the poles with any in our projection with any. So one of the ways that we can think about these nottoids is what we can do is at each endpoint, we can put in an entire vertical stick, kind of a rail that you see right here. And it turns out that the theory of nottoids as projections on a surface like the sphere or the plane are equivalent to these pictures where we prevent the nottoid from passing across the poles simply by putting these sticks in the way. And this was an idea that first appeared in a paper of Gagumsu and Kaufman, and then there's another paper by Kodakostas and Lambropolo as well. We're going to think about this instead of thinking about the sticks that prevent the knotoid from passing across the poles. We're going to think about removing those neighborhoods of those sticks, as you see over here on the right. So we can remove this neighborhood of those sticks in the surface cross eye. In this particular picture, I'm thinking of the plane R2 as being D2, have the same effect. And then I'm just going to remove a neighborhood of these poles that I have here cross eye. So my poles cross eye, I've removed a neighborhood here that prevents the knotoid from passing over them. So this is the theory of knotoids is therefore equivalent to this theory of so-called rail diagrams. In the case of spherical knotoids, we can take products of oriented knotoids. And the way I'm going to do that is because I'm on a sphere, I can always pick one of the endpoints to be in what I'm going to think of as the exterior region. And then for my second knotoid, I can think of the first point, the initial point, as being in that same exterior region. And I can just put them together and I get this product of knotoids that way. So that'll be what I mean by the product of two oriented knotoids in the spherical case. It does not work in the planar case because you can't move the endpoints to be in the exterior region. All right, so now we'd like to define hyperbolicity for spherical knotoids. And there is a definition that predates any of the things I'm going to tell you about due to Barbensi, Buck, Harrington, and Lackenby. And what they do is they take the rail diagram and they take the double branched cover of the sphere over those two rails. Of the three sphere over those two rails. And when they do that, you'll still be in the three sphere, but now your knotoid, which used to have one endpoint on the rail, is now going to have a second part on the rail, and it'll become a knot living in the three sphere. And if that complement of that knot is hyperbolic, then we define the volume of the knotoid to be the volume of the resulting knot. Okay, so that's their method. That's not the method we're going to use. We're going to use a different method. So this is method 2. And what we're going to use is this thing I call the spherical reflected doubling map. Now, the spherical reflected doubling map is I'm going to take my knotoid that is on the sphere that you see over here. So here's my knotoid sitting on the sphere. I'm going to put it over here. I'm going to remove a neighborhood of each of the poles. So I have little holes there with boundaries here and here. I'm going to take a reflected version of that up above it. I'm going to glue the boundary of this neighborhood of the pole here to the corresponding boundary here. I'm going to glue the boundary here to the corresponding boundary here. That will take these two twice punctured spheres and turn it into a torus. And so I'm going to get a projection that lives on a torus. And when I thicken that up, I get a knot living in a thickened torus. And then when I want to try to make it hyperbolic, I just take the complement of that knot in the thickened torus, and it'll be hyperbolic. Now here's the second picture of the same process, only now I'm going to start with my knotoid living in a thickened sphere with these two tubes removed from it. And I'm going to first take that thickened sphere with the two tubes removed, and I'm going to widen out the tubes to become annuli on the boundaries of a thickened cylinder. I'm going to take a reflection of that. I'm going to glue the corresponding annuli together. And again, I find myself in this thickened torus with this knot living inside it. Okay, so both of these constructions give you the same thing, only this is the sort of thickened version. This is the projection version. Okay, so then we're going to say that a spherical knotoid is hyperbolic under the reflected doubling map if the corresponding knot in the thickened torus is hyperbolic. So the complement of that knot in the thickened torus is hyperbolic. And then we'll say the volume of the knotoid is 1/2 the volume of the knot in the thickened torus, since we did use 2 copies of that of the original thickened sphere in order to get the thickened torus. Okay, so that's going to be our definition of what it means to be hyperbolic and the volume of the corresponding knotoid. Now, why do I like this definition? Well, it's really this proposition, which I'm not going to have the time to actually prove for you, but what this proposition says is if you have 2 oriented hyperbolic spherical knotoids and you take their product, the result will be hyperbolic and the hyperbolic volumes will add. Okay, now in hyperbolic 3-manifold theory, this kind of thing almost never happens, right? Most of the time, if you compose 2 hyperbolic knots, you get something that's not even hyperbolic. most of the time it's never going to work. In this particular case, you actually get that the product of two hyperbolic things is hyperbolic, and not only that, but the volumes add to give you the volume of the resulting natoid. So I think that's one of the advantages of this particular way of looking at things. Okay, so now you see here are some volumes of corresponding natoids. And again, if we wanted to compose any of them, we could just add the volumes and we could compose them to get what we want. Okay, so now we're going to generalize a little bit. We're going to look at what are called generalized natoids. And so instead of just having for each pole one strand coming in other words, the valency or the degree of the pole is 1, we're going to allow the degree of the pole to be 2, 3, 4, or even 0. So we're going to allow these so-called isolated poles. So I'm going to have a graph that looks like this sitting there. So we've got a closed orientable surface for in our case, it'll almost always be a sphere, but it could be any closed orientable surface, some finite graph. G doesn't have to be connected or simple. G can have anything. It can have these valency 0 vertices. I can also throw in some circles in there if I want, which are called constituents, and I'm going to just project it onto the surface so it has a regular projection with over-under crossings. Okay, and then what are my forbidden moves? Well, just as I had before for my vertices in the case of a natoid, I cannot move a strand across a pole, so I can't do that. I'm also going to think of these poles as being rigid vertices in the sense that I cannot just twist 2 strands that come into a vertex as you see here, okay? So this is going to be my generalization of a natoid. So as I said, I already said this, it's an equivalence class of regular graph projections with crossings up to local Reidemeister moves and isotopy, not allowing forbidden moves. Okay, so what are some examples? Well, clearly a spherical natoid is a generalized natoid with 2 poles. A planar natoid, I can think of that as a generalized natoid on the sphere with 3 poles where I put an extra isolated pole to the outside that prevents me from moving the natoid around the backside of the sphere to the other side, thereby making it as if it's really on the plane. So any classical knot or link is a generalized natoid with no poles. You can take multi-linkoids where you have a bunch of natoids all mixed together. Those are generalized natoids where the poles all have valency 1. You can take so-called n-polar knots that precede this definition, where you have a knot with poles on the knot. You can take so-called long knots, and instead of having them go off to infinity, they can go off to a pole, which again prevents you from moving anything across that pole, which previously you were thinking of as the point at infinity. So all of these examples are examples of these generalized natoids. String links, I'm not going to go into the details of string links, but you can think of string links with a single pole of valency 2n. And then I really want to focus on this idea, which is the staked links. And this is an idea where I've got some kind of a projection of a knot or link, and I've just added isolated vertices, okay? And we'll come back to this in just a second. This isn't the first time that anybody's thought about these, but we'll come back to this in just a second. Okay, so how does hyperbolicity work for generalized natoids? Well, it's going to be the same idea. Namely, what I'm going to do is I'm going to take my staked diagram. I'm going to thicken things up. Sorry. I'm going to, whoops, wrong way. I'm going to thicken up so I'm in a surface, and then I've got these stakes in here. I'm going to remove these tubes corresponding to the stakes, and some of the tubes have endpoints on them, some of them do not. I'm going to use that same trick I did when I was talking about the double map. Namely, I'm going to pull this annulus that you see right here out to the surface. So that's what I've done over here. And this annulus right here, I'm just going to pull it out to the surface. These endpoints of the generalized natoid will then get pulled out to be on the annulus there. I'm going to take that object and a second reflected copy of it and glue them together along these annular boundaries that correspond again to the boundaries of the stakes that had endpoints on them. I'm not gluing them along the stakes that don't have endpoints on them, and that's very important. So I'm going to glue these together like that. Again, I'm going to get a knot or link and a handle body, and I'm going to say that my resulting generalized natoid is hyperbolic if and only if this particular knot and this handle body is TG hyperbolic, and then the volume of it will be half the volume of the resulting object. Okay, great. So that's how I figure out hyperbolicity for generalized knotoids. Now I want to go back to the staked knots and links. As I said, staked knot or link is just going to be some projection with some particular stakes in the diagram, and you're not allowed to do the forbidden move. And when we first started thinking about this, I was giving a talk on this, and Lou was there, and Lou mentioned that there was a paper that he had done back in 1993 with Jay Goldman, where they had created tunnel links, and tunnel links are exactly this, staked knots and links. So, I was like, oh no, somebody else already did this. But on the other hand, okay, Lou did it, and he did it 30 years ago. So that means I'm only 30 years behind Lou. So I thought that was pretty good. Okay, not so far behind. So I'm trying to work my way forward. Okay, so now, the thing is, we're going to think about these staked links as living in a thickened sphere, again, with neighborhoods of the stakes removed. So you see here, the neighborhoods of the stake are removed. And you'll notice that if I take one of these tubes that you see right here, I can stretch it out, pull it all the way out and around, excuse me, until I get a knot living in a handle body. And so I'll be thinking about these staked links as living in handle bodies, knots living in handle bodies. One stake is just, if you just take one stake, going back to that previous picture, if I just had one stake removed, you'll notice I would just have a ball that this thing was living in. And of course, a ball, really, when you're looking at the theory of knots and balls, that's, I mean, I don't mean to say it's not interesting, that's the theory of knots, but that's something that's already been thought about. Two stakes is topologically equivalent to taking some kind of a component here and putting a second trivial component around it. And so that's really just sort of the theory of two-component knots or links, where one of them is trivial. So that's not particularly interesting. So what I'm really interested in is three-staked or more. And I just want to point out, if you're going to do hyperbolicity of three-staked links, how do you do it? You'll remember what we do is we take our knot living in a handle body, we double it, so we take a second copy, that is a reflected version of it, and then we glue them together along all the stakes that have endpoints on them, but none of the stakes have endpoints on them, so we don't glue them together at all. And then we take half the volume. Well, what's half the volume? That's just the thing we started with. So in the case of staked links, if we're trying to find hyperbolicity, all we want to know is the original link in the handle body TG hyperbolic? And if so, what's the volume? Okay? So that made us think we should go back to the literature and find examples of hyperbolic knots in handle bodies. So we went back in the literature, and I guess I got to admit, I was a little surprised to find out that it was a paper of mine together with Alan Reed, which is the first example of a knot living in a handle body that was hyperbolic. And so we had one example that we produced in 1993 that I had completely forgotten about. And then Frigerio in 2003 extended that example to an infinite class of examples. And so you see over here what is really a trivial link. And then you've got this graph going through it. And it's going to be the complement of a neighborhood of that graph that will give you the handle body that this particular link is living in. And he looked at those examples and he proved that they were all hyperbolic. This is, you'll notice the link is, the knot is alternating in here. They're all hyperbolic. And he found an explicit examples of explicit ways of, excuse me, ways of describing the handle body. And then one more example I'll mention in 2004, which is the smallest volume example I know of a knot living in a handle body. And then Howie Purcell in 2018, we're looking at much more complicated examples, but in particular, some of the examples that come out of their work is you can take a handle body and you can project a knot out to the boundary of the handle body to get an alternating projection. And if it satisfies certain conditions, including that it crosses the boundary of the essential disks in the handle body at least 5 times, you can actually prove that then lots of these are hyperbolic. So they generated tons and tons of examples of hyperbolic knots and links living in handle bodies. We're going to use the following result, and this is a result that I did with Joy Chen, who was one of the students that was in that earlier picture that I showed you before. And excuse me. So I'm going to start with a surface with boundary. In this case, I have a disk with 2 holes in it, and I'm going to thicken it up, and I'm going to look at an alternating projection to the intermediate version of that surface. So I'm going to look at an alternating projection in that surface. And this is the theorem that we proved. So I've got some closed orientable surface and a link in a thickened version of that closed orientable surface. Excuse me. I'm going to take a cellular alternating projection of the link. Cellular just means that the complementary regions are all disks. And then I'm going to pick a bunch of points to be my stakes. So I have a finite collection of points that are in the complement of the projection. I'm going to remove little neighborhoods of those stakes. So I'm now considering my link in this new surface where the stakes have been removed, F cross I. And then here are the rules for the stakes. First of all, I need the fact that my projection is weakly prime. Weakly prime means there's no disks like this one here, where you've got two strands coming in and some crossings on the inside that can't be reduced. Okay, so that is not weakly prime. If, on the other hand, you stick a stake in that region, then you're fine. Okay, that takes care of the fact that it wasn't weakly prime. Second condition, you can't put more than one stake in a region. Third condition, you can't have two adjacent regions, both of which contain stakes. And I really don't want you to read this fourth one, but if you have to, you can. I will show you a picture of this one in a second, but you can't have any pond path curves. If you have all of those conditions, then in fact, the complement of that link in that thickened surface is in fact TG hyperbolic. Now I want to come back to those pond path curves and show you some examples to tell you what exactly a pond path curve is. So here's an example of one that satisfies all the hypotheses. My stake neighborhoods here is drawn big here, and there's another one on the outside. You'll notice I don't have any two stakes in the same region. I don't have any stakes in adjacent regions. And then I'll explain the pond path curves in a second. Here on the torus, same thing. I've got some stakes here, no two adjacent ones, no, the projection is weakly prime. In fact, that one is good. Now, here's an example where I have one of these things that I call the pond path curve. And a pond path curve is a curve in the projection plane that passes through crossings, bisecting them. And each time it hits a crossing, there has to be a path to its right that leads to a staked region, which I'm going to call a pond, and a path to the left that leads to a staked region. So in particular, I want to think about a beautiful park and a little path in the park. And as I come along at every intersection, there's a pond to my right and a pond to my left. And I get to the next intersection, I have a pond to my right and a pond to my left. And that's a pond path curve. So in both these examples, we have such pond path curves, and they preclude hyperbolicity. You cannot have one of these knots or links in a thickened surface be hyperbolic if there is a pond path curve. Now, why? And I'm not going to go through this carefully because I want to keep track of the time, and I'm having trouble doing that. So I'm not going to spend too much time on this. But the idea here is, over here, you see in blue a pond path curve. In green, you see my knot. And I'm going to use that pond path curve and these red arcs here to create an annulus, which will be essential. And I'm going to build it. And by here, you see a little purple disc that I'm putting on right here that comes around. That's available because of the pond path curve. And then over here, a second disc I would put on over here, a third disc over here, and a fourth disc over here. And those four discs together would, in fact, create an essential annulus, which by Thurston's work means this thing cannot be hyperbolic. So I have to avoid these pond path curves. Okay, so now hyperbolicity of stake knots and links. Here's a nice fact. If you take any knot or link in the three-sphere, it has a diagram when I project to a two-sphere that can be staked to be TG hyperbolic. Okay, so you can do this to any knot or link. A trivial link, composite links, satellite links, all of which are not hyperbolic, you can stake them and you can make them hyperbolic. Now, I'm going to do this really fast because I don't have a lot of time. The trick is I want to take whatever diagram I have for my knot or link and I want to make it alternating. So what I'm going to do is I'm going to take any crossing that I want to change from what it is to the opposite. I'm going to put stakes on either side of that particular crossing. Then I can create a disk that cuts through here. I can cut the complement along this disc, put in a full twist and glue it back and change this crossing from the way it is to the opposite. So using this trick, I can take my original projection and I can turn it from whatever it was into an alternating projection. Unfortunately, in the process of doing that, most likely I've created pond path curves. So here's an example where with just 3 stakes, I could change any crossing that I want. But you'll notice here's a beautiful pond path curve that is created in the process. So to get around that problem, I'm going to do the following thing. I start with a crossing that I want to change. So I want to change it so that I can make the whole crossing alternating. I'm going to do this little move called the swirl move, where now the rest of the projection is alternating except for this new crossing over here. Then I'm going to do it a second time, a second swirl move. Everything else is alternating except for this crossing. So if I just change this one crossing here, I can make everything alternating. Then I put my stakes in here. These 2 stakes won't come near any other 2 stakes. I won't get adjacent stakes, and there won't be any pond path curves. And that's the idea. Okay, so that's the idea, that I can always stake any knot or link and I can make it hyperbolic. Okay, so now I want to think about staked lengths of 3 or more stakes, which means I do have a totally geodesic boundary. As I mentioned before, the smallest volume known is this one, so that's an open question. What is the smallest volume for such a knot or link living in a solid handle body? Now I want to specialize even more down to what are called bongles, which are very simple staked knots, coming from taking a trivial knot, putting in some monogons, and then staking each monogon. And the monogons can be to the outside, we'll call those outies, or to the inside, we'll call them innies. And the bongle can either be alternating, as these 2 are, or non-alternating. And so that original example that I mentioned that Alan Reed and I found a while ago actually is an example of one of these bongles. It's an all-outie 3 bongle. And those examples by Roberto Frigerio are all outie N bongles. And as I mentioned before, he proved those were all hyperbolic as well. Excuse me. We're going to prove that any bongle is hyperbolic if and only if it is alternating. Okay, so first, I'm going to assume if my bongle is alternating, I'm going to show that it satisfies the conditions of that theorem that I mentioned that Joy and I proved. Namely, it's definitely weakly prime. There are no regions that I have to worry about with that. Every region contains at most 1 stake because only the monogons contain 1 stake. No 2 adjacent regions contain a stake. And there's no pond path curve. If I tried to create a pond path curve, it would have to pass through a crossing like this. It would have a stake on one side, but not on the other. So therefore, it's TG hyperbolic. So alternating bongles are TG hyperbolic. Now, if I want to prove that if it's not alternating, it's not TG hyperbolic, well, the first thing to notice is if you have a non-alternating bongle, say it has an under-under somewhere, then it has to have an over-over somewhere else. So there have to be 2 non-alternating segments in the bongle. So we're going to look at cases. So first of all, here is a bongle that has 2 outies on the non-alternating segment that you see there. Remember, I said there was another non-alternating segment. I'm not even going to worry about that. I've got 2 outies on a non-alternating segment. Then it turns out I can create an annulus like this, where this region right here really looks like this over here, and these are connected together. It's hard to see in this picture. So for this one, I'm going to show you another picture that's maybe easier to visualize. And I want you to think of, you know, the long johns that they have, they're actually in this color, the long johns, and they have a little flap at the back that you can open up. Well, I've opened up that flap and pulled it up like this, and then the knot goes through this hole in, around the flap, and then back out again. This thing that you see right here turns out to be an essential annulus, and therefore it precludes hyperbolicity. So you can prove that if you have one of these non-alternating segments with either 2 outies or 2 innies on it, then in fact, you're in the non-hyperbolic situation. So we're going to assume we don't have any of those. Now, again, I said there were always 2 non-alternating segments, but now every segment has to have an outie on it and an innie on it because we're assuming none of these. So I have 2 of these here. Then again, you can build an annulus. This one's a little trickier, but you can build an annulus in this case and prove that it's not hyperbolic. So that's what we do in that case. But there is a third case, namely, it's not necessarily the case that both of these pairs are disjoint, So you could have a situation where you have an innie, then a non-alternating segment, then an outie, and then a non-alternating segment, and then another innie. In this case, the annulus is quite a bit more complicated to see, but it turns out that you can create another annulus like this, thereby proving that in all these cases, it will be not hyperbolic. Okay, so now what about the volumes of bongles? Well, it turns out that if you do switch innies to outies, keeping the same number of bongles, that will change the volume. But on the other hand, in some cases, they don't. So in this case here, you'll notice I have a 4 bongle with 2 innies and 2 outies, and another 4 bongle in a different order with 2 innies and 2 outies. And in that example, in fact, the volumes are exactly the same. And in this case over here, 6 bongles where I have 3 innies and 3 outies, 3 innies and 3 outies. Again, that gives me a case where the volumes are exactly the same. Here are a bunch of 8 bongles, and they all have the same volume. So I'm going to say that a bongle with the same number of innies as outies is called a balanced bongle. And then one of the theorems we proved was if you have 2 alternating balanced end bongles, they have the same volume regardless of the order of innies and outies. And let me just give you a quick outline of that proof. The idea is going to be we're going to decompose the complement of that knot. We're going to decompose the bongle into these octahedra. We're going to use this idea that's due to Dylan Thurston, where you can take any knot complement in the 3-sphere and you can put an octahedron between a crossing. Then you take these 2 corners, which are labeled with a U, pull them up to a point in space called U. Take these 2 corners labeled D and pull them down on either side of the knot to a point down below the projection plane labeled D. When you do that, these 2 edges labeled 1 become this vertical edge 1. These 2 edges labeled 2 become this vertical edge 2. If you do this at every crossing, you can then glue the faces together in the octahedra. All the edges get identified to other edges in this picture, and you can get a decomposition of the entire knot complement into octahedra. Okay, well, we're going to do the same thing, only this time we're going to do it for the bongle. So the first thing to notice is that I'm going to glue this end of the knot to this end of the knot to create the monogon. Now, when I do that, that's going to identify edge 2 to edge 4, edge 1 to edge 5, edge 7 will be glued to edge 10, so it simplifies my diagram, but I still have my octagon sitting there. Now I want to actually drill out the stake. When I drill out the stake, that means I'm drilling out this edge labeled 8. And when I drill out that edge labeled 8, you'll notice the edge labeled 1 will get glued to the edge labeled 2. Those will get pulled together. That edge labeled 8, which is sitting right here, will get drilled out, which collapses it down to a point. And my octahedron over here just becomes a 3-bipyramid in this case. And you'll notice that the edge 9 here appears once on the equator, and the edge 7 to the outside appears twice on the equator. So this is what's going to happen for each of my monogons. Now what I'm going to do is if I have a balanced bongle, then the number of edges that will correspond from all of the monogons that will correspond to the 9 edge will be exactly the same as the edges corresponding to the 7 edge. I'll have 3n over 2 edges on each of them. So I can choose the edges for the 3 edges around the equator to all have angle 4 pi over 3n. I will choose the vertical edges to have angle pi over 3, and then you can prove that this, in fact, will give you a complete hyperbolic structure on the bongle, irrespective of the order of the innies and the outies, that this will always give you a perfectly good hyperbolic structure. And therefore, the volume of this thing is actually just n times the volume of this particular 3-bipyramid, and independent on the order of the particular innies and outies. So here's some more pictures of bongles. Here, excuse me, I'm losing my voice. Bongles, 3 bongles through 6 bongles. I've ordered them by volume in each order. So these are the 4 bongles, 5 bongles, 6 bongles, etc. And so there's a conjecture here for fixed n. If you let k be the number of innies and you pick the innies to be the smaller of the 2, there's a symmetry here, so it doesn't matter which is out and which is in. So you pick the numbers of innies out. Then as the number of, sorry, it keeps doing that. As the number of Innies increases, the volume increases. So that's a conjecture. I'm not going to prove this next part. I'm going to skip all this because I'm running out of time. But I will tell you the other theorem that we proved is that if you have a hyperbolic n-bongle, then if its n is even, then its volume is bounded from above by a balanced hyperbolic n-bongle. So the balanced hyperbolic n-bongles do have the largest volume for bongles. And also, all hyperbolic n-bongles have volume strictly bounded from above by 5n times v tet, where v tet is the volume of an ideal regular tetrahedron, 1.01494. Skip that proof. Frigerio proved back when he was first looking at this in 2003 that if you have an all-outy n-bongle, the volume of the n-bongle divided by n approaches the same number I mentioned before, 5 times the volume of an ideal regular tetrahedron, 5.0747. We proved the same for the balanced n-bongles, that if you take the volume of the balanced n-bongles divided by n, that'll approach the same number. If that conjecture I mentioned before is true, all the other n-bongles have their volume sandwiched between these two, so therefore it would imply that for any sequence of hyperbolic n-bongles, this same fact would hold. Okay, so I am getting near the end. Let me just say a few more words. You can also talk, instead of just bongles where I had those monogons, I can replace them with two beads. Interestingly enough, now you don't need alternating anymore. All of these are hyperbolic, it turns out. So if you have a homogeneous, meaning all tangles are the same, n-bead bracelet, so you can have as many crossings in here as you want, it'll be hyperbolic regardless of alternating or not. Many of them have the same volume. More generally, if you have more interesting tangles in here, so we're going to call these charms, you can create what's called a 2n replicant of the charm, where you take the charm, reflect it, reflect it, reflect it, till you get back to where you started. So this is highly non-alternating. I call that the 4 replicant. This would be the 6 replicant. And the fact is that if you prove that a 2n replicant is TG hyperbolic, then you can define its volume of the particular charm to be 1 over 2n times the volume of that charm. And this just keeps happening, doesn't it? And then finally, there's a theorem here. I'm almost done. I'm just about out of time. That if you have a one-stranded charm, and if you're if you have a one-stranded charm, if your 2n replicant is TG hyperbolic, so is your 2m replicant for all m greater than or equal to n. So once you have TG hyperbolicity, then as you go up for other replicants, you'll get the same. How can you use this? How can you use this? Wow. How can you use this? If, for instance, I have a 4-charm bracelet here, and if each of the charms is 4 hyperbolic, namely has a 4n replicant, then the bracelet is hyperbolic, TG hyperbolic, and you get a lower bound on the volume of the bracelet as the sum of the 4 volumes of all of the charms. And that holds more generally for any 2m charm bracelet with charms, all of which have their 2m replicant hyperbolic. Okay, last thing I want to do is tell you about 2 other recent results because students are involved in these and I just want to make sure you know about them. If you want to take composition of staked lengths, this is Daniel Santiago, and we proved this fact that if you have a hyperbolic staked length that looks like this and a second hyperbolic staked length that looks like this, you can cut off this piece here, put these two together, and you can get a new staked length that looks like this. So that's work with Daniel Santiago. And then one other fact, there's an old result that goes back to Myers, and Bobby Myers proved back in 1982 a very useful result, namely given any compact orientable 3-manifold with or without boundary, it always contains a knot such that the knot complement is TG hyperbolic. So that means you can use hyperbolic techniques on any compact orientable 3-manifold if you allow yourself to remove a knot. And so my summer group this last summer, we've proved an extension of that, given a compact orientable 3-manifold with or without boundary and an integer n greater than or equal to 2. then it contains a genus N handle body instead of just a knot, a genus N handle body, such that the complement of the interior of that handle body in M is TG hyperbolic. Okay, so I will stop there. Here are some references, which I won't give you time to look at, but if you go back to the video, you can find them. And I just want to say happy birthday, Lou. And I will stop there.